Now that we've shown that a planet's orbit always remains in a single plane, now we'll show that within that plane the path is an ellipse. Okay, and we're going to start out with this constant h vector, which we had at the last video, being position vector crossed with velocity vector. So remember, that's a constant vector coming straight out of the screen towards us here. And we're going to do a rewrite on the velocity vector and just say, well, remember, velocity vector is in fact the derivative of position. All right, so we're going to have r cross r prime. And then we're going to rewrite our position vector this way. And we're going to think about, well, the position vector is the magnitude of the position vector scalar multiplied with the unit vector in the same direction, right? So, on our diagram, we can have this unit vector, same direction as r, just scaled to unit length 1, multiply that by the magnitude of r, and you get the r vector back, okay? So that's going to have us rewrite this entire thing as magnitude of r times unit vector, that's scalar times, cross product with magnitude of r, scalar multiplied by the unit vector, and it's the derivative of that, okay? Now, both the magnitude and the direction, okay, they're both functions of time that change as the planet orbits around the sun. And because of that, to actually take the derivative of this product, we have to use a product rule. Okay, so this first term, we still have r times unit vector, and crossed with, here's our product rule, be derivative of r, scalar multiplied with the unit vector, plus r times the derivative of the unit vector. And now what we do is we're going to distribute this cross product over addition. Okay, cross products distribute. You just have to make sure you keep things in the exact same order, because cross products are not commutative. So we're going to have r times u cross product with r prime u plus ru crossed with ru prime. Okay. So although cross products are not commutative, we have the scalar multiplications taking place in here, okay, the r's and the r primes. And in fact, those can come up front because they're scalar multiplied. So we're going to have r times r prime. That's just, because these are scalars, they're scalar functions, but it's regular multiplication for scalar functions then. And that result gets scalar multiplied by u cross u. And likewise, with the second term here, we're going to have r times r, and that gets scalar multiplied by u cross u prime. Now, we have a u cross u, a vector cross with itself. Of course, that gets us the zero vector. And so we can have an end result here that we get r squared scalar multiplied by u cross u prime. All right. And so that's what our h vector is. So now we're going to take the cross product of the acceleration vector and the constant h vector. Now, good question to ask is, why would you do this? Well, Newton thought of it. I didn't. So give Newton credit for coming up with this, because that was sort of the inspired piece here. So in doing this a cross h, first of all, we're going to rewrite the acceleration vector, back to what we came up with before, that the acceleration vector was proportional to the position vector. And in fact, rewriting it sort of in the more familiar way here with the unit vector, gm over r squared times the unit vector. We'll plug this in for the acceleration vector, and we're going to plug in what we got for h in for the h vector, and that's in the next video.